Okay, we are thrilled to have Professor Ciprian Manolescu to start off this year 2025 web seminar series with the talk Generalizations of Rasmussen's invariant from Rasmussen's onwards. Cyprian, to you. Thank you.
Okay, thank you very much for the invitation. It's a pleasure to speak here. So here is the outline of the talk. I will start with the definition of Hovanov homology and Rasmussen's invariant for knots in S3, which is the classical case. And then the main point of the talk will be to extend this to links in other three manifolds. So there are some specific constructions to manifolds such as S1 times D2, the solid torus, then S1 times S2 and connected sums of S1 times S2, and to RP3. So, by the way, this is a survey talk. So as you can see from the names, some of it is joint work by myself and other people, but I will also talk about just work of other people. And finally, I will discuss a general extension for links in the boundary of any compact four manifold. So that means any three manifold, but you also have to specify what four manifold it bounds. This is something called skein lasagna modules. One interesting application is the detection of exotic smooth structures on some compact four manifolds with boundary. So the main theme of the talk will be start from knots in R3, then go to knots in other three manifold, and eventually go to four manifolds. So see how knots can tell us something about four-dimensional manifolds. All right, so Hovanov homology, what is this? It's a homology theory that we associate to a knot. So it's a bigraded vector space, or it can be a link. It's a direct sum over kh I j of k. So I and j are two gradings. I is called the homological grading, and j is called the Jones grading. Okay, so let me briefly explain the definition. You have a diagram of the link, like here, and you take all possible resolutions at all crossings. So if you have n crossings, you get 2 to the n resolutions. At each crossing, you either take this smoothing or the other smoothing. Okay, so in this case, you get a square. Okay, and now you associate a two-dimensional vector space V to each circle. So here we have two V's, here one V, and so on, and you tensor them together. So here you do V times V, V, V times V, and V, and you're gonna make a chain complex out of this, like that. So this is a two-dimensional vector space. The braces just denote a change in grading. So maybe ignore them for now. And then I'm going to define some maps, the differential. So this is going to be a chain complex. There's going to be a differential with d squared equals 0. So notice that each edge in a resolution corresponds to changing a smoothing to another one. So in other words, introducing a band. Let me go from here to here. Here I introduce this band. So it can be either a gluing of two circles or a split of a circle into two other circles. Okay, so we have to define a map either from V times V to V or from V times to V times V. And you just define them by some formulas. So V is usually taken to be the span of two elements called 1 and x. And then if you go from V times V to V by gluing, then you use the multiplication on this thing with x squared equals 0. And if you have a circle split into two, then you use a co-multiplication, which is given by this formula. So altogether, this V forms what is called the Frobenius algebra. Okay, so you define this differential, and then you also have to add some signs, because otherwise everything is positive and you can't have d squared equals 0. But you add some signs and you get some chain complex. You take the homology, and that is called the Hovanov homology of the link. And you can show that it is a link invariant. It doesn't depend on the resolution. So here are some of its properties. It is an extension of the Jones polynomial. So if you take the Euler characteristic, meaning you take alternating sums of the dimensions with respect to the homological grading, and then you keep track of what Jones grading you are by a power of q, then you get the Jones polynomial. Now that's a famous invariant of knots, and this is this is something stronger. It's a vector space instead, or an abelian group instead of a polynomial. And it has something to do with 4 dimensions. If you have a link cobordism, so some surface that's embedded in S3 times 0, 1 between 2 links, then you get a map on Hovanov homology, from the Hovanov homology of the input to the Hovanov homology of the output. And you can construct this kind of combinatorially, handle by handle, like you split this into saddles, and maybe you can have caps and cups, and you define the maps using, by some formula similar to what we had before. So we can say that Hovanov homology is some sort of topological quantum field theory, but it's one for knots. So kind of you are restricted to where your knots live. They just live in this cylinder. And maybe I should say the maps compose nicely. So also to the empty link, you associate the field itself, or Z, if you work over Z. And then if you have a composition of cobordisms, then the maps compose. So it's some sort of functor from the category of not cobordisms to the category of knots, to the category of abelian groups and homomorphisms of abelian groups. Okay, so now what can we do with it? So a lot of the applications come from this Rasmussen's invariant. So Insun Lee defined a deformation of the Hovanov complex, meaning that she added some extra differential. So she slightly changed the formulas that I had. She added some more terms explicitly, and then you get some homology called Lie homology that is much simpler. It actually doesn't depend on the link, it just depends on the number of components of the link. So it's ranked 2 to the L, and you can see what is generated by one cycle for each orientation of the link. If the link has n components, then you have 2 to the L components, and it has 2 to the L generators. Okay, so maybe it sounds not so interesting, but the point is that when you have a deformation, you get a spectral sequence. And you can, from the original homology to the last one, and you can see where the generators end up so the final result, there are some generators, and you can see where they live in the spectral sequence. In other words, what is their Jones degree? So Q means the Jones degree, yes, so what should I say? So the Lie homology doesn't have a Jones, kind of by itself, it just has these generators, but if you look at how it comes from Hovanov homology, you can give them some filtration level. Basically, you get a filtration on Lie homology, and you look at the filtration level of these generators. You orient the link, and then you take the generator of an orientation plus that. There's some formula. Let me not get into the details. So this was done by Rasmussen, kind of looking at this deformation. But the point is that in a combinatorial way, you get a single number, this S of k, out of Hovanov homology and its deformation. And this number tells you something about the genus of cobordisms in I times S3. So if you go back here, you have this map, and you also have something like this on link homology, and you study how the generators behave under a cobordism. You can understand that very well in Lie homology, and you can study what happens to their to the Jones grading. And using that, it can tell you something about the genus. Okay, so let me get to the inequality. So this is what Rasmussen proved, that there is a lower, that S over 2, in fact, the absolute value over S over 2 is a lower bound on the slice genus. So the slice genus is an important four-dimensional invariant of a knot. It's the minimal genus of a surface inside the four-dimensional ball whose boundary is the knot. So the knot lives in 3 dimensions. You can ask about the minimal genus in 3 dimensions. That's called the cipher genus of a surface that whose boundary is the knot. And that's interesting. People study this. But you can also ask about the genus in 4 dimensions, and that's called the slice genus. And in particular, you can think about knots that have slice genus 0. Now, in 3 dimensions, so the ordinary genus that to be 0, that means that the knot bounds a disk. Okay, and the only knot that bounds a disk in 3 dimensions is the unknot. But in 4 dimensions, there are other knots that bound disks. So here is a knot. It's a slice, non-trivial slice knot. It's the boundary of this picture, and is basically the black boundary. And the disk is this red picture. It's an actual disk, except it self-intersects. It self-intersects in 3 dimensions by what's called ribbon singularities. But in 4 dimensions, it doesn't intersect. You can think of the color as being the 4th dimension. So as you can see here, it has a different color on one sheet than on the sheet that it intersects. So then you're fine. In 4 dimensions, this is an actual embedded disk. And yeah, this knot bounds such a disk. So it has slice genus 0. So there's also a weaker notion of topologically sliced. So I didn't say, normally when I talk about surfaces, I always mean smooth surfaces. But you can also think about just topological disks with a color neighborhood, with a nice neighborhood. And that's called topologically sliced. So now there are knots that are sliced, meaning smoothly sliced. There are knots that are topologically sliced but not smoothly sliced. And there are knots that are not even topologically sliced. And this is an important question in 4 dimensions because we don't know any general algorithm to determine if a knot is sliced. Or to determine the slice genus. So people are interested in computing it. But all we have are lower bounds, such as the Rasmussen invariant, that tell you that you cannot have it less than something. And then you can get upper bounds by actually exhibiting a surface of that genus. But to actually get the answer, I mean, in many cases you can compute it, you can get a lower bound that's sharp, but in general, we don't know. Okay, so the Rasmussen invariant really helps with this. In particular, it can tell you the slice genus of the torus knots, and actually more generally of any positive knot. This was a theorem due to Kronheimer and Mrówka. It was the Milnor conjecture, and they proved it using gauge theory, using Yang-Mills equations. And for a long time, people thought that, you really need something very deep, like partial differential equations to study such things. But Rasmussen gave a combinatorial proof, like a reasonably elementary proof using his invariant. Basically, he computed the S invariant, and it was a sharp bound for the torus knot. Okay. The other thing is you can find a topologically sliced knot that is not smoothly sliced. So you can exhibit, there is a theorem that every knot with Alexander polynomial 1 is topologically sliced due to Friedman. And then you can compute the Rasmussen invariant, you get it's non-zero, and therefore it's not sliced. And there's a construction in topology that if you have such a knot, you can get an exotic smooth structure on R4. This was another famous result that was came from Donaldson's work on Yang-Mills, and people thought you need gauge theory, but you can also do it with Hovanov homology. Okay, and then since then there have been many other applications. Plamenevskaya had some applications to contact geometry, to transverse links, and Piccirillo found knots where some other quantity, the shake genus, is different from the slice genus. And she also most famously proved that the Conway knot is not sliced. This was a knot of 12 crossings for which people didn't know if it's sliced or not. They couldn't find a slice disk, and it actually turns out that it's not sliced. Okay, so today we're going to talk about extending Hovanov, well, the Rasmussen invariant, but first let me tell you how what was the work done on extending Hovanov homology to knots or links in other three manifolds. So Asaeda, Brzezicki, and Sikora extended it to links in interval bundles over surfaces. So R3 is, well, it's I times R2, so you can project to R2. Similarly, if you have an interval bundle over the surface, you can project your knot to the surface and you can find a diagram of the knot on the surface. So then you kind of mimic the original definition and you can get an invariant. In particular, you get one in the Salitorus, which is an I bundle over the annulus. And you get one in RP3. In RP3, of course, every knot you can take out a point, and then it becomes a twisted interval bundle over RP2, over the real projective plane. Oh, and yeah, this was only with Z2 coefficients. Then Manturov and Gabrushev did it with Z coefficients in RP3. So that's kind of the simplest closed three manifold. After the three sphere, you have the real projective space. Also in S1 times S2, that's another simple three manifold, Rosansky, and then Willis got it in connected sums of S1 times S2. And then 5 years ago, Morrison, Walker, and Wedrich gave a different definition for links in any three manifold, but it's very different from this, and it's much less concrete. It's not clear how to compute it. I will talk about it. This is called the Skane-Lasagna module. So it's for a link in the boundary of a four manifold. Every three manifold is the boundary of a four manifold, but you have to specify what four manifold you have. If you specify it to be the four-dimensional ball, then you get the ordinary Hovanov homology for links in S3. Okay, so these were some generalizations, and I will talk about the generalizations of S. For each of them, we have generalizations of the Rasmussen invariant. And let me start with the first one, so the annular one. So in S1 times D2. Actually, before I start, maybe this is a good time to ask for questions, if anybody has any.
I have a very basic question, Cyprian.
Yes.
Almost obvious, but I would like to know the answer for sure. The F, capital F cobordism that you mentioned, going from one knot type to another, this can be interpreted, I think, obviously, in terms of world sheet, or F
Yes.
for me would be like time variation. And so I can interpret this picture as a dynamical picture, if that word would be necessary. Is that correct?
Yes. Yes. Absolutely. Yes.
Okay.
Yes.
So,
Yeah. So basically, we say it's a topological quantum field theory, like it varies.
exactly. When you mentioned that, well, I am in classical field theory, and therefore I tend to see if there is any way to interpret dynamically a change of topology in relation to
Yeah,
some
that's right.
governing equation. That's quite interesting. Now, also basic. On the same slide, you relate the construction of Kovanov homology to the Jones polynomial. Again, very basic question. Has this been extended to multiple variable, two variable polynomials like Homfley, PT, or other
Yes.
polynomials?
Yes. Yes. There's work of Hovanov, Rosansky. There is a home fly homology. Yes.
Okay, okay. Thank you.
You're welcome. Okay, so now let's talk about various three manifolds. So start with the Salitorus. So here we have a knot in the Salitorus or a link, and we project it. The Salitorus is an interval times an annulus. Topological, we project it to the annulus. We get a diagram like this, and we basically do the same thing. So the definition of Hovanov homology is just like this. The only thing, well, okay, you get basically two kinds of resolutions. Some that go around the circle and some that don't. And you associate to them different vector spaces with different gradings. You get basically more gradings. You get a triply graded abelian group. And Griggs, Bilicata, Verley, since you have three gradings, you can get more Rasmussen invariants. You can get a whole range of them. Basically, you can look at two of the, instead of the Jones grading, you have kind of two Jones grading, and you can take any linear combination of them and define the Rasmussen invariant like that. So you get a family of Rasmussen's invariants, dt of k for t in some interval. And just like before, we had S was giving us some bounds on the genus of not-cobordisms in an interval times S3. Now you can ask about genus of not-cobordisms in an interval times the solid torus. Again, you can make a word sheet, but from the solid torus to itself. And that's fine. You can study such things. They also gave applications to braids. I won't talk much about it, but if you have a braid, you can close it up and you get an annular link. And people are interested in various properties of braids, if they're quasi-positive or right-veering, and these invariants tell you something about that. Okay. Now, a more complicated story is in S1 times S2, or in connected sums of S1 times S2. So what is a link in a connect sum of S1 times S2? How do we draw it? Well, we draw it like this. So S1 times S2 is like you look at S3 as R3 union a point. So it's a link in here. But then you have these handles. So every time you have an S1 times S2, it's like you pick two spheres, you remove the balls, and then you identify the boundaries. So your link can go through one sphere, go outside of your space, and come out. And this is a picture of S1 times S2 plus S1 times S2. It's a connected sum of two of them. Okay, so this is a link in a connected sum of two S1 times S2s. Okay, right. Okay, so now what do you do with this? You want to define some sort of Hovanov homology from this diagram. So what Rosansky and Willis did is they inserted full twists between the strands. So from a diagram like this, you get an ordinary diagram by inserting many, many full twists. So when I draw a box like this, and I say K1, it means that these two strands or four strands, or how many you have, you like twist them around each other like K times. Okay, and they show that if you take the Hovanov homology of this, then in each grading, it kind of stabilizes. This gets bigger and bigger, but if you fix the grade, but somehow the grading range increases. If you fixed a grading, well, and you also have to do some shift depending on the K1s, then there is a stabilization. There is a well-defined limit of these things. And they show that this is an invariant of the link in the connected sums of S1 times S2. Okay, so this is the construction that works in that case. It's a little more complicated than before. Nevertheless, we can, so in joint work with Marengon, Sharkar, and Willis in 2019, we looked at the Lie deformation of this theory. And we defined an invariant for null homologous links in S1 in connected sum of S1 times S2. And again, you get some bounds on the genus of link cobordisms in an interval times this. Okay, so now if you have a link in S3, one of the things we did is we looked, Rasmussen did, so you can, he was interested in the slice genus, a surface in a B4. B4 is the simplest manifold with boundary S3. So similarly here, if you have, say, S1 times S2, what is the simplest manifold with boundary S1 times S2? If I want to look at surfaces that have boundary or not. Well, there are two natural answers. There's B2 times S2 or S1 times B3. They both have the same boundary and they're kind of equally simple. And similarly, if you have a connected sum, you can look at the boundary connected sums of S1 times B3s or B2 times S2s. So you can define kind of two notions of sliced genus for knots in S1 times S2 or connected sums of S1 times S2. And the Rasmussen invariant gives lower bounds for both of them. So before we had the absolute value of S over 2. Here we just have S over 2 gives a bound in B2 times S2. And here is, if you look at the mirror of the knot and you take minus of that, then that gives you a bound in S1 times B3. So interestingly, in S3, these two quantities were the same. S of the mirror was minus, or the original S. This is not true for our S in S1 times S2. They are different quantities, and each of them gives you a bound for the genus in that four manifold. So again, by this genus, I mean the minimal genus of a surface in the four manifold with boundary that knot. Okay, so we get this kind of properties. And another interesting thing that we used this invariant for was to say something new about the S invariant of knots in S3. Okay, so the way it works is because there is this relation between, I mean, the way we define it in S1 times S2 is to look at the diagram with many twists. And you can tell exactly how many twists you have based on how many positive crossings you have in your diagram, how many twists you need for the for this to hold, for the limit to stabilize. And here is an interesting link. So we're looking at this link in S1 times S2, where you have 2p strands and half of them go in one direction and half go in the other direction. So this has a diagram with no crossings in S1 times S2. Now, if you add just one twist, you can show that things stabilize. And one full twist gives you a torus link in the ordinary S3. And this was something for which, I mean, I'll tell you why this link is important, but basically it's hard to compute the S invariant for this in an infinite family, but using this interpretation in S1 times S2, we managed to compute it. Okay, so you can compute some new things like this torus link. Okay, and this torus link is quite interesting because it tells you, it appears when you study surfaces in CP2. So CP2 is the complex projective space. This doesn't matter too much, but we're going to take the opposite complex orientation that's just a convention. That's how people work with in this field. And we're interested in knots in S3 and their boundary in, and whether if they bound surfaces in CP2. So, I mean, of course, every knot bounds a surface in B4, but maybe you could have a knot that is not sliced. It doesn't bound a disk in B4, but maybe when you add a CP2 bar to B4, maybe it bounds a disk. You make more room by adding a manifold. So maybe I should say CP2 minus B4. Yeah, for every four manifold, you can kind of remove a ball here, and you get some four manifold with boundary S3, and you can ask if the knot bounds a disk or something else when you add this thing. So for example, the trefoil actually bounds a disk in CP2 bar, but it doesn't bound a disk in B4. Okay, so that's a more difficult question because now we're not just talking about B4, we're talking about a more complicated four manifold. But we managed to show that the S invariant also gives a bound on the genus in CP2. So if it bounds a disk in, sorry, if it bounds a surface, then the genus of that surface, it's at least S over 2. And the way we do this is we look at the core of CP2. So the way to think about a complex projective space, it's a neighborhood of the sphere, of the two-dimensional sphere. And there's a CP1 inside CP2. And if you remove it, you just get the ordinary cylinder, S3 times I. That's where we know we have the Rasmussen bounds. We have what we know about links in S3. But basically, what do you have? So if you have a surface like this, you get a cobordism from the knot. I'm drawing the knot as two dots because I have to move down in a dimension. You get a cobordism from this to something in a neighborhood of S2, which is an S3, and this is exactly this torus link. If the surface intersects S2 in 2p points, then you get a cobordism from the knot to the torus link. This is because in a neighborhood of S2, you basically have the Hopf vibration, and you get p fibers of the Hopf vibration, 2p fibers, which is exactly this link. They kind of twist around each other. So then if you know the Rasmussen invariant of this link, then you actually get bounds on the genus. You can apply what you know about cobordisms from the knot to this link, the original bounds in S3, and you get this theorem. So you can say something about surfaces in CP2 bar. Okay, great. So that's what we use the Rasmussen invariant for. And yes, so maybe I should say, what else? This was for null homologous surfaces, so surfaces that are zero in relative homology of C. Because for such surfaces, we know that it intersects the S2 in P in the same number of positive points as negative points. But then Run, a couple years ago, he extended our theorem to arbitrary surfaces in CP2 bar, or in fact in connected sums of CP2 bar, and he gave this inequality. So the Rasmussen invariant gives a lower bound on some quantity, some topological quantity, depending on just the class of the surface and its Euler characteristic. Yeah, so he computed the S invariant for all torus links with any orientation, and using that, he gave this inequality in CP2 bar. This is the kind of inequality that people proved before with in Hegardt-Floer homology. That's a different theory. But basically, yeah, it seemed out of reach for a while because CP2 bar is complicated, but yeah, and torus links are complicated, but now we can get such an inequality. Yeah, so maybe I should say like the main goal of this talk is to think about surfaces in four manifolds, where the boundary of the four manifold is a three manifold, and inside the three manifold you have a knot, and you want to know what is the minimal genus of a surface like that, if I tell you the knot.
Ciprian,
Okay. Yeah, question. Yes.
just remind me, please, what the symbol of the norm of capital sigma that
Oh, yes,
stands for what?
I didn't explain it. Sorry, it's just
Thanks.
okay, it's just the homology class. So what is the homology of a connected sum of CP2, the second homology? It's well, Z to the R, as many copies you have. So it's like you can think of it as a vector with R components, and this is the sum of the absolute values. So yeah, so the class sigma is, you can think it's a vector with R integers, and you take the sum of the absolute values.
Okay, thank you.
Sorry, I should have defined it. It's a kind of a non-standard notation, but yeah, it doesn't matter. Yeah, the point is that you can get some bound on the Euler characteristic in terms of its homology class and the Rasmussen invariant.
Sure.
Okay, so now let's move on to what? Let's move on to RP3. That's another reasonably simple three manifold. Okay, so knots in RP3. How do we draw knots in RP3? Well, first of all, there are two kinds of knots or links in RP3 because H1 of RP3 is Zima2. So you have class 0 and class 1. And each of these classes has the simplest possible knot. In class 0, you have the ordinary unknot, which lives inside R3. And in class 1, you have RP1 inside RP3. Okay, so we call them the class 0 unknot and the class 1 unknot. Okay, and if you have any link or knot in RP3, well, if you take out a point, you get an interval bundle over RP2, so you can project to RP2. This is a picture of RP2, meaning that I identified opposite points. Like this point is identified with its antipode. And here is a knot. I go like this. I come out on this side. I go like this. I come out on this side. I go like this, I come out on this side, then I end up here, and I come back where I was. Okay, so that's how we draw them. All right, so in RP3, similarly, you can define Hovanov homology. This was done by Saida Brzezicki, Sikora, Manturov, and Gabrovshek. And then a couple years ago, in joint work with Willis, we constructed the Lie deformation and the Rasmussen invariant. We got bounds on the genus of cobordisms in an interval times RP3. And we can define a quantity called the slice genus. What's the analog? So the slice genus was the bound, if you bound something in B4. Bounding something in B4 is the same as bounding, you can take out a ball from B4 from the middle, and you get S3 times an interval. So originally in S3, the slice genus is the minimal genus of a cobordism from the unknot to the knot. That's another way to think about it. And here in RP3, depending on the class of the knot, if it's class 0 or 1, we just define it to be the minimal genus of a cobordism from K to the corresponding unknot. By the way, you can only have cobordism from a knot to another knot in the same class. That's some little exercise in algebraic topology. Okay, so with Willis, we proved that, again, the slice genus over 2 is a lower bound on the, sorry, S over 2, the absolute value, is a lower bound on the slice genus in RP3. And here is a more concrete application that's somewhat interesting. We found 2 knots in RP3 that are not concordant. So what does it mean concordant? Concordant is mean that there is an annulus between them, something of genus 0. That's another question about, you can ask about cobordisms. When is there a surface of genus 0 between 2 knots? If so, they are called concordant. And we found some knots that are not concordant in RP3, but when you lift them to S3, so RP3 is the quotient of S3 by an involution, and when you lift them to S3, they become concordant. They co-bound an annulus in an interval times S3. Okay, maybe in the interest of time, I won't tell you the construction, but one of them is this knot. So we found it by computer calculation. We computed the S invariant. We did some little tricks with the S invariants, and that, well, we explicitly found an annulus in I times S3, and to show that they do not bound an annulus in I times RP3, we show that they have different S invariants. Okay, so if you look at their lifts in S3, these are called freely periodic knots. They have a symmetry because they come from RP3. And another way to rephrase this theorem is that there exists a concordance. So in S3, we have a concordance between these knots, but this concordance cannot be made symmetric. So the knots are symmetric, but downstairs they do not bound an annulus. So if they bounded an annulus downstairs, then you could lift it to a symmetric annulus upstairs. But what it says is that in S3 times I, there is this annulus that is not, you cannot make it symmetric under the involution. So that's something, that's some theorem. Okay, what else should I tell you about RP3? Oh yeah, so run. Okay, so you can ask, whenever you have a 3-manifold, what's the simplest 4-manifold bounds? And you can ask about surfaces in that. For RP3, a simple 4-manifold with boundary RP3 is the disk bundle associated to the tangent bundle to S2. Yeah, so there's a disk bundle over S2 whose boundary is RP3, and Run gave an inequality for the genus in that 4-manifold in terms of the Rasmussen invariant. Okay, again, let me not get into the details. There is also another extension. So my student Darren Chen described the deformation of the Hovanov complex in RP3, a different deformation. That's not the one that we used for with Willis. And he defined a variant of the Rasmussen invariant it's based on the Bar-Natan deformation. It's different from the Lie deformation. And then he proved an inequality for the genus of surfaces in RP 3 times I. But the interesting thing is that, okay, so one thing I forgot to say, but I should have said in the beginning, is that everything I talked about so far is for orientable surfaces. We always talked about orientable surfaces. We didn't do Möbius band or anything. So Chen gets something on a different notion of orientation, or he still needs some sort of orientable, but not oriented, but rather twisted orientable. So a surface in RP 3 times I is orientable. That means that when you lift it to S3 times I, it has an orientation that's invariant under the deck transformation. Twisted orientable means that upstairs in S3 you have an orientation that is reversed under the deck transformation. So there are surfaces that are orientable and twisted orientable. There are surfaces that are only orientable but not twisted orientable. There are surfaces that are twisted orientable but not orientable. And there are surfaces that are neither twisted orientable nor orientable. There's like two different notions. And he found a bound on the twisted orientable ones. And for example, he found a knot that bounds in RP3 that bounds an orientable surface of genus 1, but no twisted orientable surface of genus 1. Okay, so the Rasmussen invariant can, well, generalizations of this can give you this kind of applications. Okay, so now I come to the last part of the talk. Okay, maybe before I do that, any questions?
Oh, again, very simple questions. Twisted orientable is reminiscent to something like mirror symmetric. Is anything is any relation between the two? Probably not.
You mean for knots, right? Mirror symmetric. No, there is no such, well, there's no such notion in S3, right? This is a new notion in RP3. It's about the lift to S3. I think it's somewhat different.
It doesn't mean it has nothing to do with reversing orientation in the twisted orientable case, has it?
I mean, it kind of does, right? 'Cause in S3, we reverse the orientation. No, so sorry, it doesn't. No. Yeah, so mirror in S3 means that you reverse the orientation of S3.
Sure.
Here we're looking at what happens to the surface under the deck transformation, and the deck transformation is orientable on S3. It preserves the orientation on S3, but you want the orientation of the surface to be reversed. Yeah.
Okay.
Yeah.
Thanks.
Okay, so now let me talk about lasagna. Okay, you might be unhappy with I heard in northern Italy it's called lasagne, but in southern Italy it's called lasagna. So anyway, that's how it. Also in British English it's lasagna, and in American English it's lasagna. So anyway, that's what some people called it, not me. Okay, so this is something that was invented by Morrison, Walker, and Vedri. So this is a way you start with a not invariant and you get an just in S3 and you get an invariant in any 3 manifold, depending on a 4 manifold. So I have a link in some 3 manifold Y that bounds a 4 manifold. I specify the 4 manifold. And I define what are called lasagna fillings, which are, well, what do they have? So I have some balls inside the 4 manifold. I have some knots or links on the boundary of these balls. I have the original link L, and I have a cobordism from L to these links. Okay, so there's some two-dimensional object. And then I also have some labels, which are elements in Hovanov homology of these links. So the links live in S3. The original link lives in some 3 manifold Y, and we don't know how to define the Hovanov homology there, but we know how to define it for any links inside S3. So we take some elements. So the idea is to define an element for a new theory for this knot. We take all possible elements, VIs in Hovanov homology for links in S3. Okay, we look at balls inside the four manifold. Okay, and the invariant is the following. You look at an abelian group generated by all these fillings modulo some equivalence. Where the equivalence is, well, first of all, you want this to be linear, but more importantly, you can replace a ball. If inside the ball you have some other lasagna configuration like this, going to some smaller balls, you set these two things. Sorry. You set these two fillings to be equivalent. So you can always fill it with smaller balls, but you want some relation between the labels. So when you have a ball inside another ball, you basically have cobordisms in S3 times I or some other generalization. And you want this VI here to be the image of this VK or VL under the cobordism that I have inside the smaller ball. So inside the ball, we understand like Hovanov homology can give us cobordisms from S3 to, or even some union of S3s to S3, from knots in S3 to a union of S3. And whenever these labels correspond to this label under that cobordism, we set these things to be equivalent. Okay, so in other words, you kind of divide by everything that all the relations given by cobordisms in inside balls. So you look at all the balls inside the four manifold and all the cobordisms inside there, and you get an invariant that in the end, it depends just on the four manifold and the link. So this is purely formal. It sounds kind of crazy because how can you ever compute such a thing? But it gives you an invariant for links inside any three manifold. And one question is it finite dimensional? Actually, and we don't know, but it looks finite dimensional. In all the examples where we could compute it, it was, well, sorry, let me explain. It's actually, no, it's not always finite dimensional, but well, if the manifold is simply connected, then it looks finite dimensional. In many examples, it is finite dimensional. Okay, so originally in their paper, the only thing they could show was that for B4, the Skane lasagna module is the Hovanov homology if the manifold is B4. So then I did some work with my student Nate a lot. We computed in the simplest non-trivial examples, which is when you, for four manifolds that are obtained from a ball by attaching handles along a link K. So an example of this is CP2 or S2 times S2. And what we found is that you can express the Skane lasagna module as a direct limit of Hovanov homologies of the union of L. So you have a knot in the three manifold and some cables of K. So the K determines the four manifold. You attach handles on it in some way. And you have to look at all the cables of this knot. Okay, so using that, we kind of gave a general description in joint work with Walker and Vedrich of the Skane lasagna in terms of handle decompositions of the four manifolds. So this is how people study manifolds, by handle decompositions from Morse theory. And you can kind of describe the Skane lasagna in terms of Hovanov homologies of cables of a knot. It's some infinite constructions, but it looks much more computable. And using our formulas, people started computing the Skane lasagna. Sullivan and Zhang and Ren and Willis did some calculations. So you can compute it for CP2, S1 times S3, S2 times S2, things like that. Oh yeah, and maybe I should mention, in particular, it's interesting even when the link is empty. You can get, so from Hovanov homology, you get an invariant of four manifolds with boundary. Just take the link to be empty and look at all this construction with, it's just gonna depend on the four manifold with boundary. Or maybe without boundary, it might not even have boundary, like S2 times S2 or CP2. Okay, so then Morrison, Walker, Vedrich, and Ren Willis define the Rasmussen invariant. Every time you have a Hovanov homology, you get some Rasmussen invariant by some deformation. And they gave a bound, they gave this theorem. Let me not read all the details in the interest of time. But basically it works for any four manifold and any link in the boundary of the four manifold, you get a bound on the genus of a surface. So this is a very general result. It's something about the homology class of the surface, the number of components of the link, and then you have this Rasmussen invariant, which depends on the link, the four manifold, and the homology class. So this looks very general. I mean, it is very general. It has some drawbacks. One is that the definition is very complicated. I mean, it's not just, you cannot just plug it into a computer because, I mean, it uses all possible balls inside the four manifold and stuff like that. So there's no algorithm for computing S. So you can compute it in practice in some cases, like CP2 and so on, and it gives you some bounds. And the other drawbacks is that this can be minus infinity. So it can be an integer when you get an actual bound, but for some four manifolds, it's minus infinity. And then you get no inequality at all. It doesn't tell you anything. But, okay, so for example, for S2 times S2 or CP2, you get minus infinity. For CP2 bar, you don't get minus infinity. You get something interesting. Okay, so this is a general result, and it can be applied to study surfaces in every four manifold, provided you can compute this S and you don't get minus infinity. Then it tells you something. Okay, so here is a remarkable application. So in four-dimensional topology, we care about exotic smooth structures, meaning four manifolds that are homeomorphic. They're the same topologically, but they're not diffeomorphic. They're not smoothly the same. And this is the kind of question that was used to be answered with gauge theory, like the Yang-Mills or the Seiberg-Witten equations. This was the work of Donaldson from the 80s, for which he got a Fields Medal. And there's a whole area of mathematics. And it turns out that, again, you can use a Hovanov homology as a replacement. So you can detect some exotic smooth structures. And the way to do that is using this generalization of the Rasmussen invariant. So this was done by Wren and Willis using our formula for the Skene lasagna of handle bodies. So say a handle body is something that you obtained from the ball by attaching a handle on the knot. Maybe I should have drawn a picture of this, but I can do it now maybe. Let's see. Okay, so this is before. I have a knot in here in the boundary, and I attach a handle, meaning a 2-disc. Okay, and I get, well, I get something like this. It's a four-dimensional manifold. Okay, it's called the trace of the surgery. It's a four-dimensional manifold with some boundary. So from every knot, you have to specify the framing, you get a four manifold. And here are two knots that for which you can show that the traces are homeomorphic. Okay, this is some topological result. But they are not diffeomorphic. And the reason they are not diffeomorphic is because they computed the S invariance using our form, well, using what we did for manifolds obtained by handles. They looked at cables of these knots, and they found that the S invariants are different. So therefore, they are not diffeomorphic. Okay, great. So I should say that this is not kind of a new result. So with gauge theory, I mean, this is an old example. It was known that this is an exotic pair of four manifolds using gauge theory, but they gave the first analysis free proof. It doesn't include any analysis, it just uses computations in Hovanov homology. Okay, let me go briefly over what they did. What is different about these knots and how could they compute the S invariant? So they use that the first knot is a positive knot. All the crossings are positive. And for such knots, you can study the Hovanov homology of cables in the highest homological degree. This was initiated by Stošić, and but that's the property they use to be able to compute the S invariant. So there's something special about the knot. It's positive. And the second knot is also special. It's slice. It bounds a disk. So it's concordant to the unknot. And from this, you can use the cables are concordant to the unknot. And from this, you can get the computations of the S invariant. So in general, maybe I should say, for this kind of thing that where you attach a handle, you have to understand the Hovanov homology of all the cables of the knot. And that's very difficult to understand it in an infinite family, but you can do it for positive knots and for slice knots to some extent, and enough to compute the Rasmussen invariants. Okay, so I guess in some sense, it was lucky that in the literature we had this example of manifolds that are both surgeries on like traces of knots, and each knot has a special property, and the manifolds are homeomorphic. Okay, so you can also do new things, but they're more complicated. I won't give you the examples. They gave some examples of four manifolds with boundary for which you can show they're not diffeomorphic, even though they're homeomorphic using S. And people didn't know how to do that before with gauge theory. So it really gives you something new. Okay, so that's great. Let me finish with a slide of open problems. Okay, so in principle, this Kane lasagna constructs Hovanov homology and the Rasmussen invariant for leaks in any three manifold, but the definition is not very concrete. It uses all possible balls. It's something very formal and it's hard to compute. In some specific three manifolds like S3, RP3, S1 times S2, we have much simpler definition that you can plug into a computer and compute, which uses just kind of the diagrams of the knot. So one open problem is to do this for more three manifolds, ideally for all of them. But the first thing to try is to look at length spaces. So RP3 is a length space, is the simplest length space, L21, while S3 is L11. So the next simplest one would be L31. Probably if you can do it for L31, you can do it for all length spaces. And people have tried this, but we don't know how to do it concretely, like from a diagram of the knot inside the length space. Secondly, we had an inequality, the junction inequality for the S invariant. Okay, let me go back really quickly and tell you what this was. This one. If I have a surface in a connect sum of CP2 bar, then the Rasmussen invariant gives me a bound on the genus. So now the connected sum of R copies of CP2 bar is the only known closed four manifold simply connected with a negative definite intersection form. And in fact, you can show that negative definite four manifolds are always homeomorphic to one of these. But an open question is whether they are diffeomorphic. So are there any exotics RP, say CP2 or connected sum of CP2? This is an open problem. And there's some idea that maybe the S invariant could help find an exotic such thing if you can give an example of a surface in some other negative definite four manifold for which the inequality doesn't hold. I mean, if it holds in the ordinary CP2, but it doesn't hold in this new four manifold, then the four manifold would be exotic. So that's something that people are thinking about. Okay, now what else? So in RP3, we had this example of things that are concordant, are not concordant in RP3, but become concordant when you lift them to S3. You could ask, is there some knot, just one knot, that doesn't bound a disk in RP3 times I, so non-slice knot, but such that when you lift it, it becomes slice. So that's the kind of problem that, again, the Rasmussen invariant should be able to handle, but we just don't have the right example. Okay, and finally, maybe the most interesting question, gauge theory can help you detect exotic smooth structures on closed four manifolds. With the Kane lasagna, we just had like four manifolds with boundary. But we cannot really compute it that well for closed form manifolds. I mean, we can for some of them, but not sufficiently complicated. So one question is whether you can use the same thing to detect more exotic smooth structures on closed form manifolds. All right, so I will stop here. Thank you for your attention.
Okay, thank you very much, Ciprian. Very interesting talk. Questions, please, from the audience.
Hi, Ciprian. Amazing talk. Thank you very much. Can you hear me? Yeah.
Yes, yes.
Okay. Well, I got a pretty simple question. From what I can see from your talk is that the Rasmussen invariant is really well connected with the slice genus of a surface
Yeah.
In a four manifold. So these surfaces that we are talking about here are surfaces, are differential surfaces, right?
Yes.
So somehow the Rasmussen invariant is capable to detect this differential structure on the manifolds.
Yes.
Well, so far I cannot understand how that happens. How could
That's a
something that
great
is really
question. Yes.
combinatorial?
Yes, yes, yes. That's a great question. Yes, yes, it happens. Yes. So, yeah, why do you get this for just a smooth surface? So the reason is that if you have a smooth surface, you can split it into saddles and cups and caps. You have Morse theory. So you can split
I
it
see.
into elementary cobordisms, and then you can define the map for each elementary cobordism. If you had a topological surface, then you couldn't do that. So like Mike Friedman, he studied topological for manifolds and topological surface, and then they're very complicated. They're like topological, but not smooth. They are like, I don't know, they're obtained by an infinite process, and they don't look like this. You cannot break them into handles. So then you just cannot define the map.
Oh, okay, so that's the reason. Okay, I
Yeah.
see.
So somehow, even though this is differentiable and smooth, but I should mention, so every smooth manifold has a combinatorial description, and every smooth surface has a combinatorial description. You just describe it as you have a saddle here, a cup here, a cap here. You decompose it like that. Yeah.
So, well, then my question after this is it possible to define an invariant capable of detecting some other structures that are not just differential structures, like, for example, I don't know, something like symplectic structures, contact
Oh,
geometry,
yeah.
or
Yes.
some of the kind?
Yes. 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 So what should I say about that? I mean, there are many invariants like that. What do I want to say? They are somewhat different. They're not of the same kind. But yes, there are people studying Lagrangian surfaces and symplectic surfaces. They use other things like Chekhanov,
Sure.
differential graded algebras, not contact homology. I mean, there are invariants, but they're not of the same flavor. Yeah.
Oh, okay, I see. Well, thank you very much. I think
Yeah.
that's all. Uh, Amazing talk. Thank you very much.
You're welcome.
Other questions, please. Yes, I see Talia. Hello.
Hello,
Talia
hello Renzo,
Sahihi
hello.
is online, and you raised your hands. Please go ahead.
Yes, thank you. My question is, for all that scenarios included the lasagna module, is it only available or computable for the non-homologous links or?
Yes. Yes. Yes, they have to. So I mean, you can define it for the other ones, but then it's just zero because they don't bound anything.
And how do the genus band provided by this generalized invariants is compared to those given by the other known invariants like the tau invariant?
Oh,
Is it sharper?
you mean sorry, in S4 or in general? In before?
I think like they are also like generalized for this kind
Yes,
of
yes. I mean,
cycles.
but first of all, we can ask your question in before. How does S compare to tau, right?
Yes.
Okay, so in before, um, for a few years, people thought that they were the same. Like you can compute S and tau for like all the knots up to 9 crossings or 10, and they're exactly the same. But they stop being the same for some other knots, like the some torus knots actually. Like I think no torus knots are the same. No, sorry. What is the simplest knot? Anyway, for sufficiently complicated knots, they stop being the same. So then they're just I don't know. In some cases, S is stronger. In some cases, tau is stronger. Yeah, but they have similar properties. And similarly in the other three manifolds, yeah, you can define S and tau, and they're kind of similar for small knots, but they stop being the same for more complicated knots. And a lot of the properties that we're proving are just kind of mimicking what was known for tau. So it was like this was known in Hegardt-Fleur, and we prove it in for S.
Okay. And is it any perspective on the applications on the slice problem, especially for the cases that not persist to cannot be classified with others?
Um, so for what problem? Classify what?
Slice
Oh,
problem.
classify slice.
I
Yes,
think,
yes, yes. There are
yeah.
definitely knots that for which the other methods you cannot tell if they're slice, but the Rasmussen invariant tells you that that it's not slice. I mean, the Conway knot is a famous example. So this was done by Piccirillo. This is a 12 crossing knots. Actually, it's the Rasmussen invariant is still 0, but basically she found a companion knot that somehow you can show that if one is sliced if and only if the other one is not is sliced. And the other knot has like 30 crossings or something. And that one has tau equals 0, so tau doesn't tell you anything, but S tells you that it's not sliced. And then from that, you can show that the Conway knot is not sliced. So that was a new application of the Rasmussen invariant.
Okay. Thank you very much.
Yeah.
Okay, good. Other questions, please? Okay, if not, I'd like to thank you, Ciprian. Thank you for a wonderful talk. Thank you very much.
Thank you. Good, nice meeting you. Have a good
Nice
day.
meeting you.
Bye.